This video will be beneficial for the first year students studying programming for problem solving as well as for the second year students studying data structure. In array, we have already seen sequential memory allocation for the data types. But what if the data types are not present sequentially, they are present randomly? Then there must be some way to access those. So in this video, we will introduce the concept of linked list. To be more specific, singly linked list. So what is a linked list? A linked list is a linear collection of data elements called nodes. The left part of the node contains data, which can be simple data type, an array, or a structure. The right part of the node contains a pointer to the next node. The address of the first node is stored in a pointer variable called start. The null pointer in the last node is represented by cross. The linked list is also called a self-referential data structure since in this every node points to the next node of same type. In this, we will see the memory representation of a linked list. As we can see, there are two columns, one called data and another called next. The start, as we can see, is storing 1. So 1 to 10, these are the memory addresses. So the first character H is stored in 1. So 1 is stored in start. After H we can see 4. That means the next memory address in this linked list to be accessed is 4. In 4 we get E, followed by 7. In 7 we get the next character, that is L, followed by 8. In 8 we get L followed by 10. In 10 we get O followed by -1, which is null. That means if we join this total thing, then we get hello. And in between there are free spaces, or these spaces or these memory locations are used for some other purpose. Now as you can see, this simple algorithm is for counting the number of nodes in the linked list. So we have taken a variable count whose initial value is 0, and we have taken an extra pointer ptr which also contains the address of the first node, that is equal to start, because the address of the first node is present in start. Now why we have taken this extra pointer, that I will come later. Now repeat steps 4 and 5 while pointer is not equal to null. That means still the pointer reaches the last node. And count equal to count plus 1 means we will increase the value of count by 1, and the pointer will keep moving to the next node till the loop ends. And once the loop ends, then we will print the final value of count and exit. Now, as I said, why we have taken an extra pointer when start is also a pointer variable? Why we did not move start to count how many nodes are there? If we move start, then we will lose the track of the linked list. We will end up losing all the nodes, because from start we can trace the elements sequentially one after another. The start stores the address of the first node. From first node we get the address of second node. From second node we get the address of third node, and so on. So if we keep moving start, that means we will keep losing one node after another, and by the time it reaches the last node, the entire linked list will be lost. Now before we move on further, let us first understand what happens when a new node is allocated in the linked list. As I have already said, in linked list, in the data part, you can also store a structure. So here in this table, in the data part, there are two fields, roll number and marks, and the next part contains the address. So there is a start pointer which points to the first roll number, followed by 2, that means the second roll number, followed by 3, which is the third roll number, followed by 5 because it is next present in memory location 5, and so on. But then there is another pointer variable that you can see, that is avail, which is pointed to 4. Now what is this avail? This is a pointer which is keeping track of the empty memory locations. If you can see, from 4 next is 6. That means 6 number, this memory location at 6 with the address 6 is the next empty space. Then 9 means memory location with address 9 is empty. So this is also a kind of a linked list. So whenever we need a new node or new node is allocated, this first one, that is the 4, this will be allocated and this avail will move to avail next. Which is avail next? That is 6, because 6 is the next available free space. Now inserting a new node in a linked list can be broadly classified into 4 cases. Case 1, the new node is inserted at the beginning of the linked list. Case 2, the new node is inserted at the end of the linked list. Case 3, the new node is inserted after a given node. Case 4, the new node is inserted before a given node. Now we will see these cases one by one. Now from the picture, we can see that a linked list is already given and we want to insert a new node at the beginning. So that new node data part is 9. That is already mentioned. So if this new node has to be inserted at the beginning, then the next part of 9 should contain the address of the first node, and the address of the first node is present in start. So it can take the address from there, and start will now contain the address of 9, that is the new node. Let us see the algorithm for the same. So step 1 says if avail is null, that means if there is no available space, because we have already seen avail, which is the pointer variable that keeps track of the empty memory space. So if avail is null, write overflow. That means memory cannot be allocated, so no question of new node. And go to step 7, that is exit. Otherwise what happens is set new node equal to avail. Means the address of new node will be the address stored in avail. And avail equal to avail next. So avail will move to the next empty memory. Set new node data equal to value. So the data part of new node, whatever value we want to store, we will store that. And new node next equal to start. Because the next part of new node will store the address of the previous first node, which is present in start. And start equal to new node. Start will now contain the address of the new node. Now the point to be noted is start equal to new node comes later and new node next equal to start comes before it. Why it is so? Because if we join start with the new node first, then the rest of the linked list we will lose. So we will have to join the new node with the linked list first, and then we have to put the address of the new node in start. This is the next case, that is inserting new node at the end. So as we can understand, the linked list is already given and we have to insert this new node. The data value is 9 and it should be the last node now. So we will take a pointer and we will move the pointer, keep moving the pointer till it reaches the last node. Once it reaches the last node, there we will join this new node. So the initial last node, next part will contain the address of the new node, and the next part of the new node will now contain null. That is because it is the last node now. Let us see the algorithm for the same. So the first 3 steps remain the same as before. So we will see from step 4. Set new node data equal to value. So in the data part of new node we can easily give the value. So in that figure we have already seen that was 9, and new node next equal to null. Because it is going to be the last node, so obviously the next part of the new node will be null. Set pointer equal to start. So we have taken another pointer, an extra pointer, because we are not willing to move start pointer. And there is a loop. So we will repeat a certain step, step 8, while the pointer next not equal to null. That means while this reaches the existing last node. So what we will do, set pointer equal to pointer next. That is, we will just keep moving the pointer till it reaches the last node. When it reaches the last node, Set pointer next equal to new node means the previous last node next part will now contain the address of the new node and exit. Now this one is for inserting new node after a given node. As you can see in the figure, we have to insert a new node after suppose the node containing 3. So in this case there are 2 pointers. We have taken 2 pointers. This can also be done using 1 pointer, but for keeping it simple now we have taken 2 pointers. So firstly we have taken a new node. In the data part we have given 9. Now we have to insert it after 3. That means between 3 and 4. So we have to assign the pointer and pre-pointer to start. And then we will start moving the pointer and pre-pointer will keep moving next to it. That means pointer will move fast and pre-pointer just one node after that. So a time will come when pointer will reach the value 4 and pre-pointer will be in 3. So in this position we have to insert the new node. So the next part of pre-pointer will contain the address of the new node, and the next part of the new node will now contain the address of pointer. So first 3 steps remain the same. Let us see from step 4. New node data part, we have given the value, that's 9, and we have set pointer to start, which is the first, which contains the address of the first node, and pre-pointer to pointer. Now we will repeat step 8 and 9 while pointer data part is not equal to number. Means suppose we want to insert after 3. So that pointer should move until it reaches that value 3. It should reach that particular node which contains the value 3. Set pre-pointer equal to pointer and pointer equal to pointer next. This is just for moving pointer and pre-pointer. And when the loop ends and we are going to set that new node between the 2 nodes, then pre-pointer next part will contain new node and the new node next part will contain pointer. That's all. Now this is quite similar to the previous one, that is inserting new node before a given node. So suppose I want to insert a new node before a node which contains the value 3. That means basically I am entering the new node between 7 and 3. So here also we will take 2 pointer variables, pointer and pre-pointer, and we will keep moving the pointer and pre-pointer in such a way that the pointer reaches the data value 3. That means the node before which we want to insert the new node. So once that is done, so pre-pointer is present in one node before the pointer. That means in 7. So pre-pointer next part will now contain the address of new node, and the next part of the new node will contain the address of the pointer. If we look at the algorithm, we can see it is very similar to the previous algorithm. It is just that in step 7 we can see repeat steps 8 and 9 while pointer data not equal to number. Because we want to insert before a certain node, so the pointer has to reach that node, not the pre-pointer. In previous algorithm we have seen pre-pointer data not equal to number. Here it is pointer data. So set pre-pointer equal to pointer and pointer equal to pointer next. And the loop ends there. And just the next part of the pre-pointer will contain the address of the new node, and the next part of the new node will contain the address of the pointer. So next is deleting a node from a linked list. This can be broadly classified into 3 categories or 3 cases. The first node is deleted from the linked list, the last node is deleted from the linked list, and the node after a given node is deleted, or maybe a node from somewhere in between the list is deleted. So in case of deletion, there is no requirement of available space. So as we can see the first case, that is deleting the first node. So deleting the first node means what? The second node will now become the first node. So what we can do is we can take a pointer and set it to start. That means the pointer will now contain the address that is stored in start. That is the address of the first node. And start will contain the address of the second node. So it becomes the first node now. And we can simply free the pointer, that is the memory allocated to the first node. Let us have a look at the algorithm. If start equal to null, start equal to null means no address is stored in the start variable. That means there is no node. So nothing can be deleted. So write underflow and go to step 5, that is exit. Otherwise we will take a pointer variable and set it to start, and start equal to start next means start will now store the address of the second node, and then we will free the pointer which stores the address of the first node. Now this is the second case, that is deleting the last node. For that, two extra pointer variables have been taken, that is pointer and pre-pointer, and they are moved in such a way that pointer is pointing to the last node and pre-pointer is just a node before it, using a loop. So what we can do is we can set the next part of the pre-pointer as null and we can free the pointer. Let us take a look at the algorithm. The first step remains the same, and we set pointer to start and we repeat steps 4 and 5 while pointer next not equal to null. That means till the pointer variable reaches the last node. Set pre-pointer equal to pointer and pointer equal to pointer next. So we will keep moving the pointer as well as the pre-pointer. When the loop ends, we will just change the next part of the pre-pointer to null and we will free the pointer, that is the last node. So this is the next algorithm. You can see the figure, deleting a node after a given node. So in this case, we have to delete a node, suppose after a given node which contains the data 4. So if we delete the node after 4, then we have to join this 4 with 6, as we can clearly see in the picture. So for this case also we have taken two extra pointer variables, pointer and pre-pointer, and we will keep moving them forward such that pre-pointer will be in 4 and pointer will be in the node next to it, that is the node to be deleted. So we will simply join 4 with 6. So where is the address of 6 present? It is present in the node containing the value 2. So the next part of pre-pointer will now store the next part of 2. That is the pointer. So let us see the algorithm. The first step remains the same, and we take two pointer variables, pointer and pre-pointer. We set pointer to start and pre-pointer to pointer, and we keep moving them. This is step 4, which shows the loop condition, that is pre-pointer data not equal to the number. That means the node after which we want to delete. Set pre-pointer equal to pointer and pointer equal to pointer next. So we are basically moving them forward. Set temp equal to pointer, so one extra variable is taken to store the address of the pointer, and set pre-pointer next equal to pointer next means the next part of the pre-pointer will contain the next part of the pointer. That means the two nodes on the other side of the node to be deleted are joined, and we have set free the temp. So that's all about singly linked list. Every time allocating the memory sequentially is not possible, especially if the requirement is large. So the concept of linked list is introduced. In array we have certain advantages but limitations also. Advantages like this allocation is sequential, but the access can be random. In case of linked list, the access cannot be random like array. Given the base address, we cannot move on to any node we want because we don't know what will be the next address, unlike array. So that is one of the disadvantage of linked list, but other than that, there are many advantages also, because it is dynamic memory allocation and we need not so let us take a look at the algorithm. The first step remains the same. We have taken two extra pointer variables, pointer and pre-pointer. Step 2, set pointer equal to start and pre-pointer equal to pointer. Step 4, repeat steps 5 and 6 while pre-pointer data not equal to the number. That means we want to delete a node after a node with a certain value. So the pre-pointer has to reach that node. So for that, this loop is used. So set pre-pointer equal to pointer, and pointer is moving the pointer and pre-pointer. Next one, extra variable temp is used, and it is set to pointer. And now we have to join the two nodes on other side of the node to be deleted. So the next part of pre-pointer will now contain the next part of the pointer, and we free the temp. Though we could also free the pointer, it is also not required because the pointer is the node that we want to delete. Okay, so that's all about singly linked list. In array, the memory allocation is sequential, so we could allow random access. Here the memory allocation is not sequential, hence random access of the elements is not possible. But in array there is a limitation of memory. Here we can keep adding the nodes. We don't need the memory to be sequential. Wherever there is free space, we can add it to the linked list. Because whenever the requirement of memory is too big, then getting so much of sequential space can become a bottleneck. But in this case, this is the advantage. So that's all about singly linked list in this video. Thank you.